right, everyone. Today we're going to start our unit on sound. And we just got done talking about waves kind of in general. We talked about transverse waves, we talked about longitudinal waves, waves in water, we talked about electromagnetic waves, but we're going to specifically focus on sound waves during this unit. And the first question might be, how do you make a sound? And basically anything that vibrates will create sound. Of our different types of waves that we talked about, sound waves are the longitudinal waves, meaning that their particles move in the same direction as the propagation of the wave. This is like when I held the slinky and stretched it out and then pulled a couple of the coils back and then let go, and it kind of just shook back and forth. I'll show you a couple examples here of what it looks like with particles, and we're actually going to have you do a little lab tomorrow, doing a virtual simulation here. And basically air molecules, when we're talking to each other, are the things that are being pushed back and forth by the vibrations we're making with our vocal cords, or by the speakers we're using, or anything that makes a sound. Those air molecules get pushed together and they get pulled apart, and when they get pushed together, that's called being compressed, and when they get pulled apart, that's called being rarefacted. Another way to say that is that the density of the air is the greatest at a compression. The pressure is the greatest at a compression. A rarefaction is the opposite. It's where the density and pressure are at a minimum. And so here is a picture that sort of shows that. Here's a speaker, and the compressions of the air molecules, you can see them get closer together, and then you can see the places where they are apart. And then it goes in your ear, and that vibrates your eardrum, and your brain interprets those different vibrations as sound. This is sort of a cool demonstration of this. If you look down here, you can see sound waves moving from left to right. You can see clusters of those air molecules as they continue to move, but none of them actually are making that entire trip down the length of that pipe. Look at the little red dots. See how that dot just goes back and forth, back and forth. Same thing down here. And again, notice that they're going in the same direction, either parallel or anti-parallel to the motion of the wave. You can see it down here. They've got the arrows that kind of show that a little bit better, but I think that's a pretty cool demonstration. All right. We're going to skip the hearing test, but if you want to, you can go and check that out. Just be careful that you don't do it too long. It can damage your hearing. All right. What are the characteristics of sound waves? We have a hearing range between 20 and 20,000 hertz. Now, again, this is like the best hearing person in the world. Most of us fall somewhere within this range. When I have run the hearing test before, I have people raise their hand until it's, and then drop their hand once they can't hear it anymore. And almost everybody drops out about 15,000 to 16,000 hertz. And that's a really high-pitched sound that feels like it's drilling right into your brain. And then it just goes away. And the older you get, the worse and worse that becomes, because you just lose some of the elasticity in your body, and some of the ability to respond to different things. Any sound that is below 20 hertz is called an infrasonic sound. Anything above that is called an ultrasonic sound. If you've ever had an injury and you had to go get some physical therapy and they do some ultrasound on you, they put like a gel on your injury, and then they have this metal transponder that's connected to a machine, and they just rub it around, and basically what it's doing is sending ultrasonic sound waves you can't hear, but it's a wave of putting energy into that place where the wound is, and where the injury is, and it helps heal that by heating it up inside. It does a much better job than say putting a hot pack on, because heat from that kind of superficial heat can't penetrate through your skin and down deep into the muscles sometimes. Pitch is determined by frequency. So when we talk about a note being high or a note being low, we're talking about its pitch, but the physical measurable quantity of pitch is the frequency. So high-pitched sounds are really high notes, low-pitched sounds are low notes. Okay, how fast does sound travel? Sound travels pretty fast, much faster than anything that we, again, typically experience in our everyday lives. It's not a fixed quantity, though. It depends on the temperature. It depends on the medium that you're in. And even if the medium is air, it changes based on whether you're at sea level or if you're on top of a mountain, because the thickness of the air changes at different places on Earth. You can see temperature affects it. So if it's freezing outside, 331 meters per second. If it's 25 degrees, which is a little warmer than room temperature, then you're at about 346. Now notice in water, it goes a lot faster, 1,490 meters per second. That's what, 4 times faster through water? And then solids are even faster than that. Aluminum is like 5,100 meters per second. And so in the lab that you're going to do tomorrow, it's going to ask you, why do you think that is? Why would sound travel faster through these changing media? And why doesn't it go the other way around? Sound waves are spherical. The pictures I showed you were two-dimensional, but again, anytime a vibration happens, it's basically like a sphere or an explosion of energy coming out from that particular vibration. And so people in all directions can hear it. If I turn around and start talking, to the classroom, you guys can still hear me because sound is emanating, from me from all directions. Now, as you get farther and farther away from a sound wave, you can consider the curve of that sphere to be so flattened out that you can call it a plane wave. All right, Doppler effect. The Doppler effect is something that I'm pretty sure you've all witnessed before, but basically, as a sound approaches you, the sound waves are hitting you more rapidly than they would be if that sound source was staying in one place. And so if you're getting those sound waves at a higher rate, you're hearing them at a higher frequency, which means the pitch of that sound is going to sound higher. And as it goes away, every time that the source is moving away from you, the sound is pumping out of it, but the wavelength is longer, the frequency is less. The wavelength is the same, the frequency is less though, and you end up with a lower sounding sound. And this works for light waves, it works for all kinds of waves. The Doppler effect is not just for sound waves. Here's an example. And you can definitely hear the change. It's a high-pitched sound, and then right when it crosses the observer, it drops down because the frequency of your observing of the sound waves decreases. Now, if you're a person riding on that fire truck, it's going to sound the same to you all the time because there is no relative change between you and the source. Oops. All right, moving on. So here's just kind of a visual example. Here's a person, again, pretend there's a police officer inside this car. That person's going to just hear the same sound all the time. Somebody who's farther away, though, they're getting those wavelengths farther and farther apart because the source that's making it is moving away. Right? Whereas a person who's waiting for the car to arrive or go by them, not only are the waves coming out at a certain speed, but the car is moving at a certain speed, and that compresses them, and so that person hears a higher pitch sound. So here's a good visual of this. So if you look right here, you've got this stationary sound source. It's like throwing a pebble into the water, right? And the ripples just emanate outward from it. Now again, imagine this is a sphere rather than just 2 dimensions. Now let's say that there's something that just keeps tapping the water, and as that moves, it keeps making those circles, but it's moving along. And you can see how those wavelengths are compressed on one side and spread out on the other side. Now, what if it moves even faster? Let's say it moves as fast as it's able to kick those sound waves out. Now, this is sort of the situation that you see if you've ever been in a boat and you look behind the boat and you see the wake behind you. That V shape behind the boat. All those wave fronts are combining out front to create one wave front. That's the wake. And like I said, imagine this is a sphere. So, and it's not water, obviously it's air. This picture right over here of a fighter jet breaking the sound barrier is a real picture. That is a whole bunch of wave fronts of air all being in one place. That is that plane breaking the sound barrier. Now, what happens if it goes faster? Supersonic. Again, you get the same effect. Now, one interesting thing is, you hear about if somebody breaks the sound barrier, there's a sonic boom. Well, what is that sonic boom? The sonic boom is these wave fronts crashing into a person standing down or a building standing down on the ground. It's kind of like if you're standing on the beach and a boat goes by and the waves from behind the boat come and hit you. It's the same idea, except this has got a lot more energy and it's making that sound when the wave fronts of the sound crash into you because they've all been compressed into one big sound. All right, we're going to stop there for today.